data needs to be transferred, then we require 8 clocks. Okay, so in PIPO I can say we require equal number of clocks. Okay, in SISO we require double clocks. Understand? For number of clocks, same clock to input and that same clock for output, so double clock. Okay, if it is parallel then same, so same. If it is SIPO then same for input and double for input and same for, so you just don't need to get confused in this. Input would be 4-bit, then 4-bit for input, and those all bit would goes out in a single one clock because it is parallel. So SIPO would be, suppose it is 8-bit transfer, then what would be the clocks required for SIPO? If it is serial in, parallel out, and I want to transfer say 4-bit, then how many clocks required in SIPO? So see, 4-bit for input. Okay, one by one we have to send all bits, but they are serial because it is serial in. Okay, so 4-bit, and we have parallel out, so there would be 1 clock. Here we required 4 clocks because it is input is a serial mode, and 1 more clock because output is parallel mode. Okay, because it is PO, parallel mode. So we required ultimately 4 plus 1, total 5 clocks. Understand? In SIPO. They won't ask you the number of clocks, but you should clear in your mind. Okay, now let us draw this figure for left shift resistor. Okay, right shift is but obvious. We are shifting data in one manner, or what we are practiced to draw a flip-flop. Okay, now we have left shift. So you have to compulsorily draw first the architecture. Okay, and then after give names. So left shift, say it is a 4-bit or say 3-bit left shift. Okay, it is nothing described serial in, parallel out, but we generally prefer to draw serial in, serial in, serial out. So it would be bit easy option for us, easy or convenient option. Okay, so here 3 bits, so we have to draw the number of flip-flops according to the bits first. 3 bits. Okay, now look at the name, it is left shift. So whenever you heard this kind of term, in left shift, your input should be input at left side. Sorry, left shift, you are moving towards the left side. So you will generate your output at left side. Understand? So over here, what is our, we have to deal with our own actual left side. Okay, so where we'll have our output? Over here. First you need to write over here, it is serial left shift, serial output. Have to write left shift serial output. Okay, first you need to write this. Because it is very important. Okay, if you write this thing, then only you will able to draw the remaining important things. So if I'm writing our input at the left, output at the left, so my input would be obviously in right side. Okay, here there should be a clock. Okay, draw common clock first. Say in a resistor we have common clock to each resistor. Okay, and input would be asynchronous mode, one to another. Input is transferred from one to another. Okay, clocks are common. Say in any of mechanism we should have a few things common and one or two parameter as asynchronous, or which is transferred from one to another. Now here we are transferring our data from one to another. Okay, so I have to write over here, it is, what's that, this particular is left shift serial input. Understand? This particular is clock. So here we have to give name, it is AFF. This particular is BFF. And this is CFF. Understand? And this is our QA, and say if it is RS or JK, so it is JA. Understand? And we have to invert the output. Whatever input you provide, it should be inverted. Okay, in this JKFF, we have to invert JK or RS. In resistor, we have to invert this input. Okay, and then after it would be just simply forwarded to the next end. Okay, so here we have to provide one inverter. Okay, so this is done. But in left shift, we have to write our flip-flop in reverse manner. You must not see. We are habitual to write over here J and here Q. But in this case, we have to write in a reverse manner. So you should be careful. Here it would be QB and here JB. Okay, and similar way it would be QC and JC. Okay, this kind of thing. And here it would be KA, Q bar A, KB, KC, Q bar C, and Q bar B. Okay. So because it is three serial in, serial out, we require double clocks. Okay, 3 plus 3, we require 6 clocks. Okay, and if we are drawing this figure, suppose our message is 101. Okay, we are transferring data 101. So what would be the clock pulse? Okay, suppose I'm interested to draw the clock pulse. So here it is, say clock, and what is your J input, and here it is K input. So let I write, this is our clock, CRK clocks. How it should be? It is in terms of square. So we have to draw 6 clocks minimum because it is serial, so we required 6 clocks, 3 for input and 3 for output. And be careful, we are drawing or we are interested in drawing positive age triggered clocks. So it should be over here like this. So whenever we have clocks pulse, we will react on the input. We will check what is input and what should be output if we have clock provided to us. Otherwise, we won't care of whatever input provided. Okay, there isn't any meaning of input if there isn't any clock. Understand? So here we have to first draw A. At the A, FF, and next is BFF. Okay, so at first clock, what would be there in the A over here? See, first at the first clock, one would be enter over here. Then at the second clock, it would transfer to here. At third clock, it would enter into the C. And at the fourth clock, it would be at the output terminal. Okay. The second clock, this 0 would enter, and third clock, 1 would enter. And they are shifted towards the next flip-flop. Okay. So now, let I draw A. So according to the clocks, at the first clock, we would have 1. Okay, here it is 1. So it would be 1 for the next clock. Okay, here we have 1. Then there is 0, and at the third clock it would be, we have to just copy paste message 1 0 1. Okay, 1 2 and 3. At the 3 clock, these 3 bits would enter into the A flip flop. Then at the B flip flop, we have to copy this message from first clock would be nothing for this B flip flop because it won't have any input, but from the next clock it would be like this. We have to just simply draw the figure for, and the third clock CFF would have input and it would just shift. It won't do anything, it will just shift the data to the next flip flop. Okay, so this is output for CFF. So if it is asked to you to write the left shift with clock pulse, so it is not that difficult one. Okay, so this is our C line. Okay, suppose it is 1 1 1, all 1. So what would be drawn? It should be, if it is all 1, then we have to draw like this. From 3 clock, for 3 clock, it would be a big 1 1 and 1. Then next clock over here to this. Okay, don't get confused. We are shifting data would not at all work for any operation. Okay, we are not going for any of operation. It is just shifted. See, in shift or store register, store in the sense whatever value are stored, and shift register, whatever value are shift. Okay, we are not going for any of reset set kind of operation. Fine. And this is up to you whether you want to keep all 0 or all 1s. Okay, all 0 would be meaningless, otherwise anything you can select as your message bit. So this is about serial in, serial out. If you have any doubt, you can ask me. And here see 2 2 3 or 4 bit left shift or right shift register may ask you in examination. So quickly write down this. If you have any question, you can ask. And because it is age trigger, it will react on a particular age only. If you are drawing, yes, I have to draw here age. Okay, age in the sense we have to draw a triangle over here. If it is negative age, then we have to react on the negative pulse or the down pulse of the clock. In resistor or counter, you have to draw this compulsorily. And if you want to make an inverter over here, then we have to use this particular age. this particular edge. This is our downfall, so this would be treated as the negative pulse. Okay. If you have a doubt, then ask me. Have screenshot of this. See what are the important things. I have already teach you the difference between resistor and counters. So in counter, it may synchronous or asynchronous, but the input, whatever input we provide, here we have to provide input as what is message, whatever message bits or input bits are our input to JKFF, and clock is somewhat different. Okay, in resistor, our output would be the clocks for the next flip-flop. Here we have common clocks among all number of flip-flops. In counters, your output would be clock for the next flip-flop. Okay, input is not output will not treated as input to next. It will treated as a clocks to next. Okay, and there is input as voltage. Whatever a voltage provided is at the input terminal. Okay, there isn't any message bit, because you can think of the application. The resistor are used to store some information or shift some information. Okay, so we must provide some message bit. But if we are talking about the counters, then counters are used to count. There isn't any message. It is just for counting purpose. 1 to n 0 to n minus 1. So we have no message bit. So we will use our voltage as input. Okay. Suppose this is a serial or this particular, I want to convert this into the serial one. Serial in, serial out. Sorry, serial in, serial out, it is already there, but suppose I want to convert this particular figure into circular shift, then if I want to convert this in particularly circular shift, then what should I go for? We just need to provide this output to the input. Okay, this output would be provided to the first flip-flop as input. Okay, and in this case I have to forget this particular thing. Okay, so we have to say circular shift. Circular shift in the sense output of last is provided as input to the first. Okay, no matter it is first is this or this, it doesn't care. Ultimately it is inside a loop. Okay, so we must create a loop from first to last. So this is your circular shift resistor. Okay, again have a screenshot of it. So this is about the shift resistor. Now we have to go for the difficult one or complex one, that is load shift resistor. Okay, load or shift resistor. So in load shift resistor, what we have discussed earlier, it is case of parallel in and serial out. All are entered together but going out one by one. Okay, so we have the massive data. Over the period, we would have massive data to deal with. Okay, because generally the ratio should be same. Input and output ratio should maintain equal. If there is like less input and more output, or more input and less output, then it will definitely create deficiency. Okay, so here let us draw, say it is 2 bit. Okay, if it is asked to you draw PISO or by shift resistor, then until they have asked for a 2 or 4 bit, we are not going to drop for 4 bit. We have to give example for 2 bit only, because it would just unnecessarily increase the length and it would waste your time. Okay, if they have written that draw PISO for 3 bit or 4 bit, then only go for 3 4 bit. Otherwise we can draw for 2 bit only and it would be more than enough. Okay, so we have to for by shift, and both are very similar questions. Okay, just a few difference are there, so we'll notice them. So first it is 2 bits. So what is our first target? We have to draw two flip-flops. Okay, and make significant difference between these two, because it is not a normal flip-flop, normal resistors. These are complex one or somewhat different by shift or PISO. So we have to draw a few more mechanism for this. Okay, so what would be the mechanism? For say parallel in, parallel out, I have to draw over here two AND gates, two AND gates. Okay, and there is one OR gate over here. And then there is one OR gate. So the output would be provided over here like this. The output of first flip-flop would provide to this. And the output of this NAND gate would over here. And this would be here also. Okay. Now this can be our output. This may our input or output, serial in. Okay, suppose I'm entering a few data over here, then it would be input over here. And here we have one load line. Okay, and a complement of this is another line here. So we have to draw one complement. Okay. So here I have to write it is a say signal bit A, or it can over here. This is our A. Okay. So if we are talking about our left shift, this is right shift. Okay. We are shifting data towards the right. So this is right shift input. Okay. So where we have our output over here, it is RIG at the right shift output. Okay, so one thing is over, and yes, we have to provide common clocks. So here it is C LK clock. This is our common clock. Okay, and input from one would enter over here and it will goes to next. So here we can give one connection to this. Okay, so one term is over. Now what is about left shift? So left shift, in the sense we would have our output over here at this terminal. Okay, not over there. This could be our output. Okay, so what's that? We have to write this is our output and it is left shift. Left shift output. Understand? This particular is our left shift output. So where should be the input? It should be over here. Our left shift input would be over here. Okay, so here we can write left shift input. Understand? And this can be attached with the negative line. Okay, so in this case, our left shift would be in, and through this, see, whenever it is 1, if it is 1, then if it is 1, then this line would be 1 and this another complement line would be 0. So if it is 0, this particular gate is off and this one is 1, so and would have output. So if it is 1, then it will enter over here. The output input would be provided over here and processed output would be into this gate. And as this is 0 because we have complement of it, so this one is off, so whatever output would enter through this OR gate to the next and then processed and it would goes out as a right shift output. Okay, so the one flow is clear. Now what is about left shift? So we are providing our left shift over here. So at this case, our A would be 0. So complement would be 1. So this gate is working and this one is off. Okay. So whatever input is provided through this OR gate, it would process and we will have output over here. Okay. So we have to shift this output. This output needed to be shifted to the next mechanism. Okay, so for this, let I convert rather than left shift and right shift, I should convert this into the input. This is a left input. It is left side input or load shift resistor rather than shifting. I'm interested in load only. So whenever we have to we want to shift data, load or shift, this would be helpful to us, load or shift, because by shift we need same mechanism at the beginning also, load or shift. So first, if it is A, then it will load input. Okay. And here it would load. Again, this is, I can write this will also load input. This is A input, and here it would load B input. So let I try draw. It will load input. So here it is A and here it would be B. Understand? If it is 1, A is 1, so it would load to here and B will also load. And when there is A is 0, okay, if A is 0, then this line would be off. Okay, if A is 0, this line would be off. Okay, just a minute. I should convert this line over here as this line is connected with B, and this particular line is connected with bar. Okay, so if A is 1, here, if this particular A is 1, here it is 1, then this line over here, it is also 1. This is also 1. Okay, so at this time A would be enter over here, and whatever input to B would enter into this gate. Let I write it is G2, and this particular gate is G1. Okay, so when A is 1, your load would active and B will have input and A will have also input. Okay, so both are having input. But when there is a shift, for shift A would 0. For shift A equals to 0. So when A is equals to 0, this line would be 1. Here you can see, check over here, when A is 0, this line would be active, G1 would be active. So whatever output available over here would enter into the G1, and through G1 it would goes to the next stage. So it is shifting. Here we have load. When A equals to 1, you can write like this. If A is equals to 1, load operation happen, and if A is equals to 0, shift would take place. Okay, so the data would be shifted to the next flip-flop. Again it is load, then all A and B both would be loaded, and if it is 0, then from A to output would be transferred to the next one. So this is your load shift figure. Okay, it is known as a load shift or PISOC. Then after, once you draw this, you have to give name over here. It is JA, then Q. Here it is JB and Q. And we have to compulsory, as it is resistor, we have to compulsorily draw inverted input to the next one. This should be drawn compulsorily. So here it is nothing but KA Q bar, KB Q bar. Okay. I have just drawn the same. You can draw for this 2 3 resistor, it is 3-bit resistor, then we have to draw this similar figure over here also. But load shift, so load type, all would be loaded, A, B, C, D, whatever flip-flops you have, all would be loaded together. And then after, in the shift, this second gate would be off and first gate would be work. G1 or G3 would work and forward data to the next one. Okay, so this is load shift figure. If you have any doubt, you can tell me. See, we have to make this mechanism. We have load shift and we have complementary line which is alternatively connected. Okay, and here it is G1, G2. So one is connected with complementary line, one is with original line. That's it. Okay, and same figure, we have same scenario for the next one, that is next is our bi-shift resistor. So in bi-shift, here it is bi-shift. Okay, we have only 2 minutes remaining with us, so please rejoin it.